Hey guys, sorry I'm late today. Okay. So, oh, let me show. Sorry, my video. Okay, cool. Welcome everybody. Um, uh, so I posted. I didn't finish grading yet. Almost done. I should be done by tonight. But I tried to give some feedback, and hopefully you guys also saw which ones you missed. I would say about half the class probably got close to a perfect, and the other half definitely struggled a little bit with the concepts, which has been pretty much my experience with giving this first midterm. And I think with these concepts, once you kind of get the main idea and you feel really comfortable with it, you can ace all the questions. Um, so what I'd like to, when I finish and return the exams, what I'd like for you guys to do is um, just make sure you know how to answer the ones that you missed, and like you can either review somebody's solutions or ask for help, and then when you do your corrections, uh, you know please try to first learn what you did, how to fix the mistakes, and then uh, kind of the next day or something like that, just try to redo those questions, just sitting alone, without any notes, just making sure that you know how to do it rather than just copying the correct answer. Um, and then also kind of explain kind of what you learned by doing this approach. Uh, and I will give you some points, and then for a few students, I would like to schedule like a retake in the future as well, and I would open that up to anybody who maybe got below, even after the so you'll get some points back with the corrections, but maybe if you want to get more points, I can let you do a full retake. And the retake would be like it wouldn't hurt you. It could only help you type of situation in terms of the points. And at the end of the day, like all the stuff with these test points and stuff, like that's not my main motivation. The main motivation should be, okay, I want to learn this really, really well. And so maybe I'll just give you a similar test to make sure you can ace it, and make sure that you've mastered those concepts. All right. So let me just first ask, were there any kind of, yeah, let me first ask about, I want to mention two things today about the test. Did anyone, I didn't quite see, but did anyone have any ideas about the bonus? Here, notes, duplicate. So anyone have any ideas about the bonus? Which was to show that, what was it? The actual bonus here. Classroom. Sorry. All right. So so the first bonus is bonus number 1. Why do powers of 11 show up in Pascal's triangle? Anyone? One student had a kind of nice idea, and welcome to share. But anyone have any thoughts on this one? And you're welcome to either raise your hand or chat, and then I can call on you. And feel free to like just blurt out any idea. It doesn't have to be the right idea. So just to remind you guys, Pascal's triangle is the one that has the expressions for all the binomial coefficients. So 1, 1, 1, 2, 1, 1, 3, 3, 1, and then 1, 4, 6, 4, 1. Anyone have any ideas? Does this, first let me ask, is this always true? Like this is like how could we explain that this is happening? This is 11 to the 0. The next one is 11 to the 1. 121 is 11 squared. 1331 is 11 to the 3rd power. And then you can check on the calculator that that's going to be 11 to the 4th power. So why is this surprising? How can we explain why this is happening? Chester, go ahead. What do you think?
What I kind of like thought about this was like a palindrome effect, so like how forward and backwards it's the same sequence.
Mm-hmm.
And kind of like how like how like the 11s are kind of like that sequence as well.
Oh, that's true. Okay, that's a good observation. Um, so um, uh, it is a palindrome, and we do know that. Remember the thing with combinations. So the thing with this Pascal's triangle is that it comes from a row of combinations, and we know that like 6 choose 1, for example, is the same as 6 choose 5, because 1 and 5 add up to 6. So like these numbers that are matching on like the opposite sides of the middle, they are always kind of the same. They have different, they're different, they look like different combinations, but they're always the same. So it's true that 11 is also a palindrome, but that might not explain necessarily, like if we did 33 different powers of 33, we might not get the same sort of result. I'm not sure what the powers of 33 are, but but that's a good observation. Yes, it is a palindrome, and it's nice that 11 is also a palindrome. I'm not actually sure if let's just try 33. Let's kind of do an example. Maybe there is a pattern. I would not be surprised if there's something interesting. So I'm going to do 33 squared, just an example of doing another palindrome. 33 squared So Chester, 33 squared here is 1089. This is 11 to the fourth. So first, what do you guys think? Does this pattern go on forever? Uh, Here.
Just like it going on forever. I don't think it necessarily could, just because even in the next row you have double digits.
Ah, very good.
So that just doesn't seem to apply, although I might be like there might be a way to manipulate the double digits by a certain rule that still applies, if that makes
Excellent.
sense.
Yes, definitely. So there's a nice observation that, okay, wait, so we have the 11 to the fourth is 14641, but 11 to the fifth, well, that's, if I write it here, this is going to be one, probably should have given myself 1, 5, but now it's a double digit, 10, 10, 5, 1. And so these numbers are not really digits, they're 10 things. And let's just try it out. Let's do 11 to the fifth. I'm going to do it in Google right here. 11 to the fifth. What do I get? I get 161051. So, Kieran, do you see any way you could explain kind of what's going on here? Like, why is this seems to, the pattern seems to have broken down. So what's a way you could explain what's going on?
I'm not exactly sure, but if you like, just like a funny pattern, if you add the first three digits and then just keep the rest constant, it still works. But I don't exactly know. I don't know. My idea for like compare, like relating 11s to these kind of had to do with like binomial theorem.
Good, okay.
Um, well, I mean, obviously, but sort of like I was trying to think of what, and it just represents like, I don't know. It's hard for me to explain, but I was looking at the one like for 11 squared.
Uh-huh.
I was looking at the 121, and I thought of it not as like 121, but as like 100 plus
Yes.
plus one.
Yes. So let me kind of highlight your idea. That's you're right there. You have the key idea, and you can actually see it in. You're just like you're 99% of the way there. So, Kieran, how did you think about 121?
Um, when I do multiplication, I like to split it up into like tens and ones and stuff because
Excellent.
it's easier. So
Right.
I was trying to split up that into 100 plus 20 plus one.
Nice. Okay.
Um,
And how did you how does this relate? Why is this the same as 11 squared? How do we see that if we're breaking it up?
um, yeah. Well, I mean, you could kind of break 11 squared. I was trying to compare this using the formula a plus b squared equals.
Yes.
So I was trying to break 11 into a plus b, but I couldn't really think of, and that's where I got stuck, and that's where I'm stuck now, if that makes sense.
Yeah, okay. So once you see it, I think you'll be like, "Oh, that's obvious." Can you see how to break it up into a plus b? This has to be 11 total.
Oh, oh, it's 10 plus 1.
It's just 10 plus 1. That's the key insight. 11 is 10 plus 1. That's all you need to know to answer this pattern. So why is 10 plus 1? Why is it being 10 plus 1 so special? Well, let's do the binomial theorem. This is like our a plus b, right? This is like a squared plus 2 choose 1 times ab plus b squared. And do you guys see how it fits into that pattern? you want to try it? Just kind of play it out for 11 to the fourth. So let me. I'm just going to scroll down. So what I want everyone to try now is just use the binomial theorem to expand 11 to the fourth, which is really the same as 10 plus 1 to the fourth. So expand this using binomial theorem and see what happens. And hit yes when you have finished expanding it. Or you can think of this as your A, and this is as your B. Nice. Anybody else finish expanding it? We've got one student so far.
Want us to solve it all out too?
Yeah, we'll just make the observation. Like, what's interesting about this? You don't have to solve it all, but you know, for the fourth power. By the way, it's good to just have those memorized, like 1331 for something to the third power, and 14641 for something to the fourth power. Those kind of show up sometimes, and it's just nice to know them as a general thing. Right. So when we expand this to the fourth power, you guys can see that you get 10 to the fourth plus 4 choose 1, 10 to the third times 1 to the 1, I'm just going to do 1, plus 4 choose 2, 10 squared times 1 squared, plus 4 choose 3, 10 times 1 cubed, plus 4 choose 4, 10 to the, 1 to the fourth. And what do we know about these numbers that we're highlighting? What's nice about all these numbers? They're all just powers of 10 that are decreasing because the binomial theorem makes you drop one exponent and the other one goes up, but the other number is a 1, so it doesn't change the actual thing. So this just stays as different powers of 10, but we know that when we add different powers of 10 and in front of them is a single digit, it's just the digits place. It's just the desired digit. So then this will simplify as 1, 4, 6, 4, 1. 14,641. All right. So now that you've seen it, what do you think about this?
Well, because each one's a thing to the power of 10, it pretty much just gets, it's going to be like when you have the fourth digit, it's just 4 followed by 3 zeros.
Exactly.
So all that matters is the 4 choose 1 or the 4 choose 2, and that's why it's the same.
Exactly. And is it clear now why it breaks down for the fifth row?
Well, it doesn't really break down for the fifth row.
Exactly. Yeah. Quentin, how can you explain kind of how to maybe adjust the fifth row?
Well, when you have something like 10, that's basically just 0 and carry the 1.
Yes.
So in the digit next to the 1, 5, you would just turn that 5 into a 6, and then there's still a 0 there. But then when you move 1 to the right, you have another 1 you're being carried. So it's 1, 6, and then 1 again. But then there's nothing being carried to that slot, so it's just a 0.
Exactly. Excellent. So, beautiful. So the pattern kind of still holds true, but it loses its like the pretty part of it where you can just read it off from Pascal's triangle. But you can still kind of think of carrying over the numbers for larger rows. And I'll post something. There's a lot of really fascinating things in Pascal's triangle. One of them is if you take the triangle, and you know how we may have like an equilateral triangle? If you move all the ones to the right side and look at the different columns that way, you get a bunch of neat stuff. So let me show you on the next page. And I'll just leave them for you guys to think about. And, you know, people are still discovering Pascal, like people are still discovering patterns in Pascal's triangle. It's a really rich mathematical object. Yeah, so this is 1. Let's do 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. This one is 1, 5, 10. No. Yeah, 10, 10, 5, 1. These are just the things with the rows. You guys notice anything? I'll do one more. Where is it? 1, 6, 15, 15, 6, and 1. You guys, there's a bunch of interesting patterns here. Do you guys see anything interesting?
1, 2, 3, 4, 5, 6.
Okay, that's a good one. This is just the sequence consecutive numbers. Very good.
3, 6, 15, and 4, 10, 20.
What about those?
The fact that they're the same, either direction, the same sequence going diagonal and vertically.
Oh. You mean Alex? You mean this pattern here? These guys and these guys?
Yeah.
Okay, cool. So those so first, what's the good explanation for 1, 2, 3, 4, 5, 6?
It's just like, and I like to think of it as a triangle again, but it's just like that slant. And then you can also see the other slant in the 1, 2, 3, 4, 5, 6 going diagonally. And that's what Alex was also seeing.
Exactly. There's a connection between kind of things that are along the hypotenuse and things that are on the vertical leg, because that comes from the palindrome effect that we know from before. So that's a good observation. And the consecutive numbers as well is pretty interesting. Yeah. So have you guys ever heard of something called the triangular numbers? Does anyone know what that is?
I've heard of it before. No, I forget.
Here, I'm going to write a pattern and see if you guys can come up with a formula for it, okay? So you start with 1 dot, then you draw 3 dots, then you draw some more dots. So, um, what do you guys think about these numbers? How many dots are there in this first picture?
A couple.
A couple. Well, less than a couple here. How about in the second one?
3.
3. This one,
6.
the bigger triangle,
10.
and if I were to do the next triangle, what would the pattern be?
15.
15. Nice. So these are called the triangular numbers because if you arrange a lattice of these kind of equilateral triangles and you make each side, each edge can have a certain number of vertices and you count the total number of dots, you get something called the triangular numbers. This is a really neat fact. What is a nice way to, and this is something that you might have done in algebra. Do you guys know a convenient way to calculate these numbers? Like if I said, what's the 7th triangular number? What's the pattern you could do to calculate that? So the 7th one would be the one where there's 7 dots on the bottom.
Would you just
7
use
plus 6 plus
summation?
5 plus 4 plus 3 plus 2 plus 1.
Yeah, nice logic. Yeah. So these numbers are related to adding together consecutive numbers. So for example, the number 10 comes from 1 plus 2 plus 3 plus 4, right? Which is 10. And then from algebra, do you guys remember what this is called? Adding 1 plus 2 plus 3 plus 4? Do you guys ever? That would be if it was multiplication, but this is just adding them.
Quadratic.
It is a quadratic pattern. That's true. You guys ever see this in you might not have seen it in algebra, but there's and this is a nice kind of thing for standardized tests to know. What's a trick? Let me just go up here. So have you guys and hit yes if you have and no if you haven't. Have you guys heard of what an arithmetic sequence is? Okay, so half and half. So arithmetic sequence is just a type of sequence that a sequence of numbers. So you have A1, A2, A3. This is a sequence of numbers. We call this a sequence of numbers. This is just a general sequence. And an arithmetic sequence is a special type of sequence that's evenly spaced. So for example, the sequence of numbers 5, 8, 11, I'm adding 3, 14, and so forth. This would be an example of an arithmetic sequence. And there's a pretty nice formula. I'll just share an article later and you guys can read about it. How to find the sum of an arithmetic sequence and how to, there's all these types of problems you learn in algebra about how to find a certain term in an arithmetic sequence. But I don't want to go too deep into that. I just want to show you the most basic arithmetic sequence. Or it's also a linear sequence, yeah. Lydia made a good comment that it's a linear sequence. It's the same idea. We have something called the difference is 3. So 3 is the constant difference. There are many types of sequences. A sequence can be like the digits of pi, for example, will form a sequence of numbers. That's a totally valid sequence. You have also sequences that grow exponentially. That's an example of something we call a geometric sequence. So there's a lot of sequences, but in particular, the sequence of consecutive numbers is really special. It's a type of arithmetic sequence, and it's a very pretty one because there's a few different ways to think about it. What do you guys think about this? What if I wanted to, without doing too much work, add up these numbers, 1 plus 2 plus 3 plus 4, all the way up to 100? So, anyone have any thoughts? How can I do this without kind of plugging it all into a calculator?
You
Go
could
ahead,
do, oh wait, did someone else say something?
No, you go good.
Okay. Yeah, I think Quinton's probably saying this, but you could add like rainbows of them almost. So like 100, 99, and 2. And when you do that, like the equation you essentially get is n plus 1 if n is your like greatest number, and multiplying that by n over 2.
Excellent. Yeah, we have n numbers, and we know that because they're all evenly spaced, and this is the cool thing, even if it's even or not, right? We know that they're all evenly spaced, so we know the average of all the numbers, of evenly spaced numbers is the first plus the last divided by 2, because that's just the midpoint. So the average of all of them is this. Okay, and then if we have this, if we have the average of all the numbers and we want to figure out their total, this is just equal to the average times however many there are, or times n. This is equal to the total. And in this case, 100 plus 1 is divided by 2, which is going to be 50.5, times 100, which is 50/50. All right, so the total is 50/50. But what's a little bit more interesting here is that the formula is interesting. Do you guys recognize this expression? N plus 1 divided by 2 times n. Do you guys recognize that as any sort of thing that we've seen?
Can you scroll down just a bit?
Yes. Oh, no, I cannot. Is that a little bit better?
Yeah, it is. Thank you.
Does anyone recognize what n plus 1 times n over 2, maybe I'll put a little 1 here. Does anyone recognize if this is something that we've seen? What's another way of writing this expression?
N squared plus n, right?
N squared plus n over 2, that's right. But is there something related to combinations? This is the way we can think about this as combinations.
Is it like m plus 1 factorial over 2 or something?
Similar, okay, very close. And not exactly n plus 1 factorial, because that would have a whole bunch of other things. But what is it? You're really, really close, David.
Okay.
Like n plus 1 factorial divided by n minus 1 factorial divided by 2?
Yes, that Lacha, you're correct. Is there even simpler formula for? But you what is that? That thing that you just said. What is that really?
It's like NC1 almost. right?
Kira, you're very close. It's not NC1. NC1 would just be N.
Oh wait.
Oh, n plus 1 C2.
It's N plus 1, choose 2. Right? Because remember, you count down, if N plus 1, choose 2, you count down one spot, and you go there. This is just N plus 1, choose 2. Okay, now this, do you guys believe that this might explain a little bit why it's showing up in Pascal's triangle? Right, because these numbers that we found, the sum of the arithmetic sequence, they are in this row. So let me ask you another way to think about what was this one? This row, for example, let's focus on. I'm going to do a new. I'm going to copy and paste this whole thing. Oops, where'd it go? Small. All right. So let's just focus on this number, this 10. This 10 comes from 5, choose 2. Which we just saw is 4 plus 3 plus 2 plus 1. Okay. Can anyone kind of connect these two facts? Why is 4 plus 3 plus 2 plus 1 the same without doing the calculation? Obviously, we know that when you multiply the left side and you add up the right side, they give you the same number. But is there a way to connect what's happening on the left side, which is if you have 5 friends, how many ways are there to invite 2 of them to the movie to the movie, with what's happening on the right? And maybe instead of inviting friends to go to the movie, you can think of another way to frame it is if you have 5 friends, how many ways are there for 2 of them to shake hands? Where the order doesn't matter. How many handshakes are possible? So I'm going to draw a picture here of a pentagon. So how many handshakes are possible? Do you guys agree? Hit yes if you agree that I can use 5 choose 2 to calculate the number of handshakes that are possible. Awesome. And I'm not talking about total like diagonals, I'm just talking about overall handshakes that are possible, or edges that are possible to draw. So we're not doing like the subtract 5 things. Okay, so that's 5 choose 2. Can anyone explain, and I think you guys have actually, somebody actually did this explanation earlier. Why is this the same? Why can I also do 4 plus 3 plus 2 plus 1 to calculate it?
Because you can't shake hands with yourself.
Okay. But if you didn't know about combinations, why is it 4 plus 3 plus 2 plus 1? Like how could you get it another way if you didn't know combinations? If you just started drawing it out?
Because the first person A can shake 4 of their hands.
So A can shake 4 hands.
And then B can shake 3 hands since he already shook hands with person A.
Excellent.
And then C is there's 2 other hands. D and then D has only 1 other option.
Excellent.
Meaning E has no options.
And E has already been accounted for everybody. Awesome, Adam. Very good. Alex, that's right. There's 4 other people, and you just count that way. So I just like this because it demonstrates the idea that when you see things in 2 different ways, one is just kind of picking 2 out of 5, but the other one is adding up how many hands from starting from each edge, you get really nice patterns and really nice formulas. And anytime you encounter math, it's really, really valuable to see it from as many ways as possible. Okay, and then let me show you one other thing here. Let's see here. Where was it? There was some really nice article. Yeah, I'll post this here. Okay, this is where it gets a little bit trippy. So the first, this pattern here, this row of numbers, or this column of numbers, these are the number of dots if you had an edge. Like if you have an edge of length 1, it's just 1. Or sorry, if you have length of edge 1, it'll be, you have 2 dots. If you have length of edge 2, it's 3 dots. Does anyone want to take a guess? And this is a hard one to guess. And by the way, the very first column with all ones, that's the number of like 0-dimensional things. Does anyone want to take a guess what the column of numbers 1, 4, 10 represents? 1, 4, 10, 20. Nice, Quentin. Yes. Which 3D object do you think it's going to be? And maybe we could draw one of them just to see that it actually works out. I actually haven't worked on it too much, but I think you could come up with some similar explanations. Anyone want to take a guess which kind of 3D object in terms of dots, or what like the outline would be for the third column? Sorry, the fourth column. So now thinking about this column. Anyone have any ideas? So the last column that we did was called the triangular numbers. There's square numbers, there's pentagonal numbers as well, but the next column is a little bit different. It's interesting.
Pyramid numbers?
It's a pyramid, but it's a very special type of pyramid.
Special pyramid numbers?
What's the simplest type of pyramid you can think of? Do you know another name for it?
Wait, is it a triangular prism?
Kind of. It's a tetrahedron. It's like a pyramid, but with a it's a type of pyramid, but it's one where the base is specifically a triangle. So you start off with 1 dot. That works. Do you guys see that this one has 1, 2, 3, 4 dots? All right, and now the next one I actually never have drawn it myself, but do you guys believe if we try to, how many of these could we stack to make the next thing? I believe, you put one there. You definitely extend this over, so it'd be another dot there. So we have 3 there, 4. Yeah, so it's I have to think about this. Can you stack? I don't know if you can actually stack them like that. Let me look it up. Okay. It's on Geeks for Geeks. Oh, okay. So yeah, so it's actually not that hard. So all you do is you extend the shape a little bit further down. And now you have a new triangle at the base. But the idea is that each of the faces makes a triangular number. So yeah, 1, 2, 3. Oh, something looks a little bit off. Oh, my bad, my bad. This picture is a little bit off here. Let me change this up a little bit. Like that. So you have 1, 2, 3. That's your original tetrahedrons on the top, and then if you extend it to the bottom, you add another 6 dots here. 1 like this. So 1, 2. So this would be a total of now 10 dots. And then the one below, you would keep extending it. You would do another thing. So on each face, you have like a triangular number type of configuration, but then the edges match up. So that's the tetrahedral number. And I'll post this if you guys want to take a look. This is a good example of it in the chat. And then 1, 5, 15, that would be in the fourth dimension. So, and yet this pattern can keep going on forever. So it would be something with 4 points or some sort of similar shape like a triangle, but in 4 dimensions. So yeah, there's a lot of neat stuff in the Pascal's triangle. And let me see here one other thing here. And the last thing that I want to show you, then this is really, really fascinating, is and each of these, like I didn't explain like why the tetrahedral numbers show up. That I encourage you maybe to think about. And if you want to discuss it later, if you have some questions, I'm really happy to. The other one that's really, really cool no. So the other one that's really cool is if you look at the diagonals. So do you guys know this sequence? So if you add up all of the diagonals, this would be 1, 7. Do you guys recognize this? So, and I'll kind of write these boxes in here. So what do you get for the first diagonal, the very first? Anyone want to volunteer to read out all the sums you get? Well, let's do it together. The very first one, the 1 is just 1. The next one is 2. All right, what do we get after 2?
3.
3.
3. After 3?
5.
After 5?
8.
After 8?
13.
13. After 13?
21.
Nice. And last one?
34.
34. Excellent. Do you guys recognize those numbers? Or what's any interesting pattern with those?
Every number is equal to the past two numbers added up.
Exactly. Nice. So like 5 is 2 plus 3, 8 is 3 plus 5.
It's the golden ratio.
Exactly. It's related to the golden ratio. And do you know the name of the sequence, Griffin? Exactly. It's a Fibonacci sequence.
Yeah.
So this is one of my favorite facts. The Fibonacci sequence, which doesn't seem that related to binomial theorem at all, is actually baked into the triangle in a sort of a really sneaky way. And so I encourage you, this seems like a really mysterious fact, and it's very beautiful. And I encourage you just to kind of try to think about why it's true, and you could even, if you're stuck, if you're curious, you can try to look up and try to find an explanation of why the Fibonacci sequence shows up in the triangle, and then try to understand it. I really encourage you to do that, and I'm happy to explain that as well. All right. So these are just some cool sequences. But going back to the other extra credit problem, that was talking about why do the rows add up to a power of 2? And we went over this. So so why does the nth row? Let me erase it. Let me write it right here. Why does the explore? Okay, why does the nth row add up to 2 to the n? Anyone want to volunteer their idea here? Griffin, did you say something? What's a good idea? So like we know that the second row adds up to 4, the third row adds up to 8, and so forth. What was the idea that we saw? I saw a few of you got this part.
Since every row is made by adding up the 2 diagonal above it, right? It would be double the last.
Nice. Okay, so that's a really good insight. Is if you know the addition rule for Pascal's triangle, you know how to make the next row from the previous. The sum of the next row, it will always be twice the previous row. And if the very first row is 1, then it's going to keep being powers of 2. That's a very good inductive explanation, but it does require us to explain kind of that thing that we saw, like why the addition rule works. But can you do it without the addition rule, without kind of referencing the previous row?
I don't know, maybe this applies, but if you think of like just binomial generally speaking, and you think of it as plus b to the n.
Yes.
If you think as a and b both as 1, then
nice.
it just kind of works. And I
Exactly.
think that probably relates to just like the choosingness, like essentially if like n is equal to like 4, you're going to be doing like 4 choose 0 all the way to 4 choose 4.
Exactly.
And
Right,
then
because the powers of one don't matter, right? Because it's just like a one.
yeah.
That just goes away, and at the end you're just so that's really good. Nice here. That's a really good way to see it as binomial theorem. So far we've seen a few different ways. So Quentin shared the idea that with the addition rule, it's clear that the next row is counts the previous row twice. And if you start with the first one, then it's always going to be doubling. And Quentin suggested, okay, if you do 1 plus 1 to the nth, you can FOIL it out using binomial theorem, and you see that you just end up with the binomial terms and the plugging in a and b as 1, those expressions don't matter, and you're just left with adding up the rows of the triangle. And we know that 1 plus 1 is 2. Awesome. And then the last explanation, do you guys remember this? Why is it clear that n choose 0 plus n choose 1 or whatever plus n choose n all the way should be 2 to the n? What's with that ice cream problem? Why is that a clear way to think of that? By just kind of explaining like what you're counting, or a different way of counting. And I think you guys explained this before. This is the number of subsets on the right side. Of any size. And to make a subset in general, you have to go to each item and you have to say yes or no. You have two choices, and you have to make those two choices n times. That's why it's 2 to the n. Okay, very good. So I just want to show you one last pattern with binomial coefficients, and then see if you guys can explain it. And then we'll move on to the next idea. Actually, yeah, one last pattern. So, so let's say we have Alice, Bob, Cindy, Dan, and Evan, and Frank. So we have 1, 2, 3, 4, 5, 6 people. The question is, how many odd subsets are there? And how many even subsets? And like an odd subset is just a subset of like the 6 friends that has an odd number of people. For example, if I pick Alice, Bob, Cindy, I would count that as one odd subset. So I'll give you guys a few minutes to think about this. And when you got the number of odd subsets and the number of even subsets total, let me know. No people is no people 0 is even. So if you have the empty set would be considered as an even subset. Nice. All right, we got one person. All right, a few students have a good idea. If you finished okay, Adam, how did you calculate the number of odd subsets? Oh, Adam, I can't hear you.
My bad, I was muted.
No worries.
So there's 6 different things.
Mm-hmm.
And so for each of the odd numbers, I did 6 choose that number.
Nice. So 6 choose 1. And what did you get when you added all these up?
6 plus 20 plus 6, so 32.
Awesome. Okay. Now, how many even subsets are there? How did you approach that one?
I mean, I could have just done the same thing I did for the 6s,
Mm-hmm.
but I thought it would be a little quicker if I just did 2 to the power of 6 minus
Nice.
32.
Excellent. So I'm going to write out the longer way, but that's right. Whatever is not odd, whatever subset's not odd is even. So you got to just take the 2 to the 6, which is 64, subtract whatever you got. That would be the remainder. Awesome. That's a good shortcut. But this is the pattern. 6 choose 4, and 6 choose 6. This is also equal to 32. And what's the interesting observation here?
Why is it equal to 32 even when you have 6 choose 0, which is 1?
Yeah. Okay, so 6 choose 0 is 1, plus 6 choose 2 is 15. 6 choose 4 is also 15 because it's same as 6 choose 2, and 6 choose 6 is 1. So those all add up to 32. So if we tried this pattern, so we got the same number on both sides. Have you guys ever heard of the term conjecture? So anyone want to volunteer what conjecture means? Conjecture is like something you think, like a pattern that you think might be true, but you're not quite sure why exactly. So, oh, okay, no worries. If you guys have to run, so I'll leave it here. This is true also for 5 things. If you did A, B, C, D, E, you would find that 5 choose 1 plus 5 choose 3 plus 5 choose 5 is equal to 16. And the same thing with 5 choose 0 plus 5 choose 1, plus 5 choose 2 plus 5 choose 4. And this example is not as interesting because you can check that a lot of the numbers are the same. Like this is the same number, these are the same number, and these are the same number. So over the weekend, we have a few patterns here. And what I'd be really happy is if any of you guys over the weekend can, I'll post these notes. If any of you want to try to either explain the tetrahedral number pattern or the Fibonacci pattern, which is maybe a little bit hard, or the this pattern, these are all kind of food for thought for the weekend. And then I can kind of go over some of the ideas on Tuesday. This stuff I won't really be testing on this. So this is just I could tell that a lot of you guys, just like me when I was in high school, were pretty intrigued by this subject. It's one of my favorite subjects. So I wanted to kind of show you some more stuff about it. But next week we will move on forward into probability, and then after that we'll get into statistics. But this is just kind of a bit more in depth in these combinations. So I'll leave you there to explain this. You actually have all the tools you need if you want to investigate this further. This example, everyone now has all the tools to explain why this example is true. We actually did a very similar example twice earlier, or similar technique twice earlier in today's lesson. So I'll just leave you with that hint. All right. Do you guys have any questions? Awesome. So this is really focus on this you're welcome to think about this if you felt really comfortable with the test. If you didn't feel too comfortable with the test, don't worry about the stuff that we did today. Just try to work on maybe reviewing some of the notes, watching some of the Khan Academy, asking some help for the corrections and stuff. Yeah. And if you need any help also, you're welcome to email me as well. All right, guys, well done. I will be giving out info on the retake when I return all the scores. And for now, I'll just have you guys do corrections. Retake will be maybe some point in the future. After I review your corrections, I'll kind of talk to you individually maybe about doing the retake.
For the corrections, what form do you want them turned in? Do you want us to just like write it down on paper and scan it like usual?
Yeah, exactly. Yeah, just write it down and upload it to the corrections assignment.
How many points do we get back for corrections? Or like,
yeah, you should get back. What was the test out of, like 12 or 13?
12.
Is that out of 12? Yeah. I'll try to get you back up to a 10. If you got a really low score, do the corrections. I want to see them, but I might require a retake. Like if you were below a 6 or 7, I would like just to see. We'll schedule a time to just do a retake, just to make sure you feel comfortable with the ideas. But yeah, if you just missed a handful, you can get up to a 10. maybe I'll also. Oh yeah, if you don't need if you feel happy with your score, you don't need to mark anything. You're welcome to upload a correction if you feel like there's one that you made a mistake. You just want to say, oh, this is what I did wrong. I'm always happy to see that. I'll give you a thumbs up, but or maybe even half a point. Maybe I'll make the highest like with corrections be like 10.5 out of 12. What is that? Like just maybe just below A. 10.5 divided by 12. Oops. Yeah. So if you got below a 10.5, you can submit corrections, and I'll give you some points back. All right. And the scores, Lily, the scores will be given, I hope, by today. Maybe tomorrow. I finished grading most of them, but I do have some meetings left. Cool. Did you guys enjoy these patterns? I know I didn't get to explain them, but do you find them interesting? Awesome.
Yeah. Today's lesson was really cool.
Awesome. Yeah. I'm glad you liked it. All right, guys. Have a great weekend, and I'll see you on Tuesday.
Thank you.
Bye.
Thank you.
Thank you.
See you, Kieran. Well done.
I just had a quick question.
Yeah.
I know for mine, for one of the problems, I accidentally wrote a fraction line when I meant combinations to make a correction.
Yeah. I gave you full credit. You did a great job.
Okay, cool.
I do that too sometimes.
Yeah, yeah, they're just on top of each other. I did that a lot on like practice.
It's just like a hard habit to break because you just I don't know why. I think it's just we're so used to writing fractions that it happens. It happens. Yeah. Well done.